So good morning. Talk the one before last, already late for lunch, so I will try to be as quick as I can, focusing on the main parts of this presentation only. What we have done for this work is to measure cirrus clouds during the campaign using the LiDAR during the campaign of Chuva Sul. So we are trying to look into the radiative forcing from this type of clouds that we know will have a large impact on the long wave, but not so much on the short wave. And at the end, try to estimate what the impact on the ground and on the top of the atmosphere. So it's a work that we started earlier this year, and it's still ongoing. And this is the main site. We choose 4 golden days, golden for Cirrus observations, not for the precipitation events. And these are all in November 2012. So he had helped us to locate these days, and we analyzed with the algorithm for the LiDAR inversion that we have developed at Physics Institute. And this is the instrument. So I already talked about the LiDAR and how it makes measurements yesterday. And so this was the site at Santa Maria. It's the very same instrument that I presented yesterday. And here you can see the LiDAR signal and a small cloud layer on the mid-troposphere. So how the algorithm works? For the first part that we had to do is to identify the clouds. So in a general sense, what you do first, this is a schematic view of a signal. A real signal has a lot of noise added on top of that. So the first part is to detect all minimums and maximums. Then you do a gliding average, and the curve will look like this diagram. And then you compare the difference from the top to what should be the base if the cloud was not there, with the amount of noise, looking at the future and unfiltered data. So you decide if that's a real peak or not. Once you do that, I can define a molecular region below the cloud, a molecular region above the cloud, and I can do the LiDAR inversion and look at the backscatter coefficient. From the size of the backscatter coefficient, I can then decide if this is a cloud or an aerosol layer. Of course, at the heights that we are looking at, it's never going to be an aerosol layer anyway. And for doing the inversion, the results presented here is during daytime, so I can only use the elastic channel and perform a usual flat inversion. So I had to assume a LiDAR ratio, which is a proportion between the backscatter and extinction, and it's 18 stereo-radians for these from previous studies of cirrus clouds at these latitudes. And this is one of example. This is the first day. So this is observations at UTC times around noon, from 15 past 11 until 1:30. And that's the more or less the Santa Maria site on these MODIS images. And you can see fairly easy the positions of the cirrus clouds. And that's the LiDAR observation, just the corrected signal. And it's between 10 and 12 kilometers. And the algorithm does work. So if you look at this part, it's between detecting the cloud base at 10, a cloud top somewhere at 11.7. So it's corresponding to this part. And at the end, we also detect the base and the top of the cirrus clouds. And the red curve just indicates the height where the most strong signal is coming back. To make sure of these observations, I had a look at data from Calypso. So unfortunately for these days, Santa Maria is around here. So we are almost as far as possible from the end of these tracks. I took this one, I think, during daytime, and that's what's shown here. So for the latitude at this Santa Maria site, we are talking about minus 30 south. It's, I think I have something here. So it's more or less at the same height that we observe in the Cirrus clouds at Santa Maria, which is okay because these are advected and as they are transported. So we are indeed seeing what we should be seeing. This is just the Calypso mask for this day. So it's identifying it as a cloud and identifying it as a nice cloud. Actually. Second case, at the end of the month, November 28th to the 29th, around midnight. And these cirrus clouds start very high in the atmosphere, then goes down. And again, the modes images for that. These we can see not near the site, but it's not at the same time. And we apply the algorithm, detect the cloud base and the cloud height. And we do the same for the others, which are not shown for the sake of time. Okay, so this is the Calypso. We see at the same latitude the Cirrus cloud showing up at the same altitude that we are seeing at the site. For this one, it's much closer to Santa Maria, the overpass of the satellite. And these are the cases that we have identified during the campaign. Nice and good measurement. So the cloud base, the lowest that we detect was 80.5. Sorry, 6.8. And the top at 8.5. And the highest about 12 kilometers in the atmosphere. Then I didn't show, but using the CLET inversion, the inversion of the LiDAR data, we can calculate the backscatter. If you assume a LiDAR ratio of 18 stereo-radians, I can calculate the extinction and do the integral over the cloud and calculate the optical depth of these clouds. So these are the range between 1 and 2 values. And then yesterday night, I thought it was good if I could show at least some estimations of the radiative impact of these clouds. So I went online. This is one of the radiative transfer models that you can find online. So if the students don't know about that, just copy or check on Google. This is cohort, but you can also find an online version of SBDART. So for the first case, an AOD of sorry, not AOD, it's an optical depth, not an aerosol optical depth, but at noon local time, I had to assume spherical ice, surface temperature of 32 degrees. It's just a standard mid-latitude summer profile. Many assumptions that I actually need to use real Chuva data for this analysis and not just some wave enhanced calculation. But if from the results of the radiative transfer model, I ran the model with and without the clouds for both the short wave band and the long wave band. And for this first case, we found a forcing on the top of the atmosphere of minus 42 watts per square meter in the short wave cases, indicating more reflection and cooling of the column. And the long wave is trapping 80 watts per square meter of long wave escaping from the Earth. And smaller values on the ground. So on the ground, if you add these two, for the whole column, the Cirrus is doing what it is supposed to do, which is warm the system, while it's cooling the surface. Right? The plan is to repeat this, not with an online tool, of course, but using the data from Chuva, the actual profiles, the measurements of the water vapor, and so on. And do instantaneous calculations along the lifetime of the Cirrus and see what's happening and try to look at other time as well and not just the golden Cirrus base. So for that, we will need to do some integration with other measurements, try to estimate the effective radius for these ice crystals in some better way. And that's it. So it's more plans for the future to conclude this work than actual real new results. Thank you very much.
So we have time for one question.
Yeah. Yeah. I didn't check for the very same time, but no. I mean, the ones, the pictures that I saw, I didn't, but I didn't see it. But I didn't see it as truly as I looked at my own LiDAR image. So it might be there. And,
Good.
diba? We are on the way of doing that, trying to look before and after, but then we need to get our hands on or get the help of someone with the radar data and or maybe with the train data and to look and try to find the sources of these clouds. But it's planned as well. But
Yeah, we see very different. The integrate. What's the number? It's ice water patch.
from the radar.
From different Cirrus type.
Yeah,
Twice the difference of.
In this case, this is a very simple calculation. So what I did was to, because I fixed the radius in 70 microns, then I don't need the liquid water path because I have the total optical depth. So it's a constraint. But
Yeah.
we need.
Okay, thank you.